Or one option is you take the exam separately.
Mm, it's okay.
It's okay?
It's okay.
So then let's keep it the exam for next week, Wednesday, and we'll find another time for you. Uh, So we are waiting for Subyang and one other person. So did someone see Subyang? I saw her 10 minutes ago. Now she disappeared. Maybe she's around. She has 1 minute left. So today I brought two exam subjects from the previous year. Essentially they are similar, but there are a few different questions. Well, in the previous year, a typical question I gave was, or I gave first a tensile an engineering tensile stress curve, stress strain curve. So it looks something like that. And I was asking the student to indicate all parameters which we can extract from such a curve. So by all parameters, I mean obviously the Young's modulus, the yield stress, the ultimate, the UTS. We would have here the fracture stress. So correspondingly, we have fracture strain. Here we would have the plastic strain. What else do we have? Well, here we have the necking. And here we would have, if we consider this area, we would have the resilience modulus. Which is 1/2 of sigma y epsilon elasticity. Or we can rewrite it using the Hooke's law, so we know that, in other words, we have 1/2 of E epsilon to the square. Here we would have, if we consider now this area, we would have the toughness. Which is roughly sigma fracture times epsilon fracture. Here also it would not harm to mention that in the plasticity regime, so here we have Hooke's law in the elasticity regime, and for elasticity, and for plasticity, we have sigma so note it on so if n is equal to 1, again we go back to the elastic case, and if n is equal to 0, we have an ideally plastic material, and if it's in between, we have a work hardening or work hardening material. Did I forget anything here? Oh, and then, so this would be the first part of the problem, and in the second question, I was asking, how can we transform an engineering tensile stress strain curve into an how we call it, into a true stress strain curve? So we remember that the engineering strain is or actually we call it E usually, but it doesn't really matter, is delta L over L, or we can write it is over L0. We can write it is dl over L0 from 0 to L. From L0 to L, sorry. And the true strain is given as ln of Le over L, or in terms of integral we can write it is dl over L. So that it's really the instantaneous length. That's why we get the logarithm out of it. And the relation between is ln E plus 1. Okay, so this would have been a typical question. I will give you or I can upload if you want the subject. So I was, for Sugyang, I was mentioning in the previous year, I have very often asked students, or I have given students an engineering stress strain curve, and then I was asking to provide all parameters which can be extracted from this curve. So we have the Young's modulus, the yield strength, the elastic limit or the elastic strain, the UTS, the necking, fracture strength, and the fracture strain, plastic strain. Then we can extract the resilience modulus, which is the elastic energy we can store, or we can also extract the toughness, which is the area below this curve. What we can mention is also the elastic or the governing law for elasticity, so Hooke's law, and the governing law for plasticity, which is called the Hollow-Mons law. And in the second question, second sub-question, I was asking to relate the true strain with the engineering strain, so as to transform this curve into a true tensile stress strain. And basically we get this value. Okay, another type of problem would be that I give some values of Young's modulus and yield strength for different material, and asking to calculate the resilience modulus. So basically using that equation. Or it's not that equation in that case, sorry. In that case we need to write, and now the resilience writes 1/2 sigma square over E. So it's fairly easy. Let me switch that off. Since we don't need it. Okay, another typical question would be on the dislocation motion. Then I was asking to describe and explain the different mechanisms of motion for an edge dislocation. So we have basically two mechanisms. The first one is the gliding, where we have, say, let's make one more. So I would basically have a dislocation here. And if I apply a stress, this atom would be more attracted to this one, and now would move below here. Now our dislocation would have moved, or would have, now the dislocation would be here, and then it continues one step and so on. So there is one slide on that where it's well explained. The second mechanism is the climbing. In that case, we have, again, our items. So again, we would have our vacancy here. And now we have two possibilities. Either this atom moves into a vacancy. Now our dislocation has moved one step up. Or this atom could move here to create a vacancy, and now our dislocation has moved one step down. So note, climbing always needs dislocation. And to have dislocation, you need a temperature, you need heat. So you probably don't need to mention it, but just to remind, the equilibrium concentration of vacancy is So it's basically the energy of formation of a vacancy, or the exponential of minus the energy of formation of a vacancy divided by the thermal energy. So the more temperature, the higher the temperature, the more vacancy you have. So, and it's, as a rule, or it's not a rule, it's a fact. As a fact, vacancies are the only defects in a crystal that are at thermal equilibrium. That means they don't have an excess energy. Dislocation, they always have an excess energy. Grain boundary, same. Dislocation, you cannot avoid them. They are at equilibrium. They don't have to be, but there is always an equilibrium concentration of vacancies. Okay, another in my mind, very important thing to remember is to consider the mathematical expression or expressions for the friction stress to move a dislocation. So usually I ask, or in the past I have asked, to give those mathematical expressions and to explain the difference based on those equations between the motion of dislocations in a FCC material or in a BCC material. So for tau, for the frictional stress, which we can write tau F, we can either write it is PB over A, or similarly we have an alternative equation that writes it is PW over A. So remember, so this is the interatomic distance. This one is the interplanar distance. And this one is the width of the dislocation. So from this equation, we can already deduce that if A goes high, tau F goes down, and if B goes down, tau F goes down. So that means that dislocation move on most densely packed planes along most densely packed directions. So typically for, can I delete this one? FCC, this location will move on the 111 surfaces along the 110 directions. And for BCC, oh, actually we need to write something like this to be correct, since we are using the families. And for BCC, we would have 110 and 111 directions. Well, so this is what this equation indicates. Now this equation indicates that if, oh, wait a moment, I did a mistake somewhere. I did a mistake, I'm sorry. And this is the interplanar. So this is, interplanar, and this is interatomic. So now in the case of the width, we have if W goes up, tau F goes down. So in the width of a dislocation, we can understand as or let's call it R is the distance from the dislocation. And here we would have the displacement. So, and we go from B over 2 until minus B over 2. And here we would have the position of our dislocation. So this would be the case of a narrow dislocation. And in the case of a wide dislocation, we would have something like this. Blue is not working. So interestingly, this is especially important since for FCC, W is always large. So the core of dislocation in a FCC material is always big. And it does not depend on the temperature in FCC. In BCC, the width is it strongly depends on the temperature. So if we have And this is the main reason why BCC material have a brittle to ductile transition. So, yeah, really based on these two equations, there is quite a lot to tell. Uh, okay. Okay, then I was in another question. I have asked, I have set a simple problem. I was asking students to consider a glide plane on which we would have two different dislocations. So with opposite sign. And we have discussed that in the case of H dislocations, or we can consider H dislocations as a dipole. So the reason is if we consider our H dislocation, here we would have compressive stresses, so we would be minus, and here we will have tensile stresses. So now, if you want, we would have a plus and a minus, and here a minus and a plus. So dislocation of opposite sign, they will attract each other. So they will move. So now the question is, what happens once they meet each other? Well, basically they annihilate. They destroy each other. So you can imagine you have one extra half plane here, one extra half plane there, they meet, it makes a full plane. In another situation,
So will be no more dislocation.
no, there will be no more. They will annihilate. They will cancel out. So now what happens is if we have a dislocation on this plane, and on the plane below, we have a dislocation of opposite sign. They still attract each other. But what happens when they meet? When they meet here?
There will be gap between them
Yeah,
according to
Exactly.
the strengths of them.
So we'll have a stacking fault,
Yes.
typically. Note, we could draw it for this case also. Now we would have an extra piece of plane in between. Only in this region. So this would also be a stacking fault. Yeah, this was short problem. And then a last typical question usually involve okay, then I was asking, draw and explain typical stress strain curve for BCC single crystalline metal at different temperatures. So if we had considered the case of niobium in the lecture, so again we would have gamma here and tau here. at low temperature, we know that our yield strength is very high. So we will have something like this. At lower temperature, it will rather look like something like that. So T0, T1, and if we continue decreasing, we will have something like that. And if we continue, something like that. And we have so then we could explain that it looks basically this way. So here we have here we would have in here roughly here. And on the other hand, we have, if we consider only tau, we would have, here we have G over 300. So here we have our, so one is the easy glide, here we have work, hardening, and in 3 we have exhaustion. Hardening. Yeah, alternatively, I could ask also to draw it for FCC material. So for so note this is for BCC. For FCC, it would look slightly different. We would have so here we would be at say T0, T1 and T2, or actually we need to continue much more here. And we have T2. The important part is that the critically resolved shear stress is always same. It doesn't depend on the temperature. Yeah, this is usually what I ask. So each time there were 4 questions. Maybe what I would like to show at least once. I will probably not ask for it during the exam, but once I have asked students to express the volume change during plastic deformation as a function of the Poisson ratio.
Function of delta N also.
Yeah, so basically you need to consider that if we write V0, it's L1, L2, L3.
Cubic and
Yeah, well, you can consider it, they are different. L1 does not have to be equal to L2 or to L3. And for the final volume, we would have L1 plus delta L1, L2 plus delta L, and L3 plus delta L3. Or in other words, so then we need to develop that.
And delta L1 multiplied delta L2 is almost zero. Or
I'm sorry?
if we multiply delta, multiply delta.
Yeah, we consider they are so small, I mean each are so small that they vanish. So we would have something like L1, L2, L3 plus L1 delta L, oh, we need to check, delta L, wait a moment, L1, L2 delta L3 plus L1, L3 delta L2 plus L2, L3 delta L1. So now we can write that delta V is simply L1, L2 delta L3 plus L1, L3 delta L2 plus L2, L3 delta L1, 1. And now for delta V over V0, we now have L1, L2 delta L3 plus R. Plus L1, L3 delta L2 over L1, L2, L3. So those two, they cancel. Tac, 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 tac. So we get it is basically
Delta L1 over L1, delta L2
yeah.
over
So we have
L2.
epsilon 3 plus epsilon 2 plus epsilon 1. And now in the case of the axial tension, we remember that epsilon 2 is equal to epsilon 3 equal to the Poisson ratio times epsilon 1. And now we obtain for delta V over V0 that it is 2 times the Poisson ratio plus 1 epsilon 1. So that means that there is always a volume change in elastic deformation unless the Poisson ratio is 0.5. So the smaller, is it correct? Ah, there's a minus somewhere. Sorry. 1 minus 2 Poisson. So if the Poisson ratio is very small, we will have a very large volume change. The maximum value of the Poisson ratio is 0.5, cannot be larger. Otherwise, we would have a negative volume change, which is impossible. So, do you have question to this, or I think it's fairly simple? It would be questions of the same kind. I remember that students always had problem with this. Maybe difficulty to visualize, but in fact it's very simple. You have a dipole, plus plus repel each other, plus minus attract each other, and yeah. It's a simple geometrical problem. And the rest, yeah, I mean, just, there are really very few equations you need to remember. So the frictional strength is one equation, or are two equations you have to remember. Some question could involve Holloman's law. So you should remember, or remember also that if we take the log, we get log of k plus n log epsilon. So yeah, so these are equations which are easy to remember. So I can upload those if you want.
Yeah.
Yeah. So I will upload in a moment. Yeah. So to remind, it's a pity one student is missing today. So exam will be on Wednesday this week. Are you available?
Next week?
Yes.
I'm okay. Next week, Wednesday.
Yeah, coming week, next Wednesday. And when would you be available? So maybe Thursday?
Okay.
Is okay?
I have a lecture, I mean normal class from 2 to 5.
From 2 to 5. We can meet in the evening if you want.
Okay.
Okay, at 7 or... Okay. Oh yeah, maybe don't forget to bring a calculator. for if there are numerical problems. Wow. And yeah, calculator, I will bring the paper, so don't forget your pen.